Hi everyone. Today we're going to talk about the matched t-test or the paired samples t-test. This is from chapter 11. So to think about when you're going to be using the matched t-test, here's a few examples of situations. So first one, Dr. Filburn wishes to assess the effectiveness of a leadership workshop for 60 middle managers. The 60 managers are rated by their immediate supervisors on the leadership rating form before and after the workshop. So the key was the same people are going to be measured with the same outcome variable, in this case a leadership rating form, before and after the workshop. Another situation, Dr. Clark is interested in determining if workers are more concerned with job security or pay. He gains the cooperation of 30 individuals who work in different settings, and ask each employee to rate his or her concern about 1, salary level, and 2, job security on a scale from 1 to 10. So this one may not be super obvious from the way it's phrased, but it's the same people that are working in one setting and working in another, and seeing what their responses are to these variables based on where they're at. So again, the same people, not necessarily before and after, but the same people in different settings. And this last one is Dr. Gale questions whether husbands or wives with infertility problems feel equally anxious. She recruits 24 infertile couples and then administers the infertility anxiety measure to both the husbands and the wives. In this case, the couple are connected, so the husband and the wife can be treated as a pair. They're going to influence each other's scores, they're going to have a lot of similarities, so we actually can treat them as a matched pair. So for the most part, when we're using t-tests, we're going to be using it when the same person is measured in multiple situations. But sometimes we're going to be able to do it when the pair is matched, like this situation. So paired samples designs. And essentially what we're trying to do is comparing means of two groups where the assumption of independence has been violated, resulting in a dependency across the groups. So we can't call them independent groups anymore. Instead, they are dependent groups. So this can happen when you have members of the same family, the same classroom, group, litter, twinship, all these things where they are connected. Or when it's the same person in multiple situations or multiple time points. The variance of the dependent variable is smaller as the groups consist of same or closely matched cases. So we can't use the same approach because we're violating assumptions and things will be different than what we're actually wanting to test. So if we're using the independent samples t-test, our groups should be independent of each other. There shouldn't be any influence on them. So if we were using the same person at pre and post test, those two groups are not independent as the same person. So there should be a lot of similarities between them from pre to post. Now note the paired samples t-test is also known as the matched pairs, related samples, correlated samples, dependent samples, non-independent samples t-test. It's also sometimes called the repeated measures t-test. They're all saying the same thing. Of course, in stats, we just like throwing out as many synonyms as possible. So when you think about the paired samples t-test, there's multiple ways that this can happen. It can be through experimental design, where you actually match people or decide to test people pre to post, or in different settings, the same people. Matching helps when you can't provide both conditions or both time points to everybody. There's also the naturalistic, and this is just when the samples are naturally connected, correlated, or dependent on each other in some way, like spouses. Usually this is when I see the the paired samples t-test, it's when you have the repeated measure design. So you have two measurements, conditions, or sets of stimuli that are applied to cases sequentially, so before and after, or in other words, longitudinal designs where you have a pre-post or time 1, time 2. In some of these repeated measures designs, what you're doing is looking at the effect of being in one group and then the effect of being in another. These are called crossover designs because often there can be what's called order effects. You need to counterbalance the order. So a random subset of the cases in your group would have A and then B, and then another random subset. Everyone else that didn't get that first, the A then B, would get B and then A. So that would help you understand if there's a difference if you get A first and then B, or if you get B first and then A. One thing to note is that counterbalancing may not eliminate all the carryover effects. So if A or B is something that somebody holds on to, whether it's some intervention or it's some learning, whatever it is, then counterbalancing is not going to eliminate carryover effects. But it'll help you know a little bit about whether A is carried over or B is carried over. One approach to this is using what's called a washout period. So you give it enough time for the effect of A or the effect of B to wear off before you give the other. You also can use what are called simultaneous designs. So we just talked about successive designs where it's from pre to post or time 1 to time 2. Simultaneous designs is two varying conditions or sets of stimuli intermixed within study, and all cases receive both. And this is where you have no concern for order effects or temporality, and the order is just generally random. So you can really use either one, successive or simultaneous designs, depending on how you are thinking about what is actually going to happen from time 1 to time 2. So when it comes to the hypotheses, what we're going to be looking at is the direct difference method. And what this is actually going to do is it's going to simplify things for us. So if we're looking at the independent samples t-test, you've seen this one before where the mean of group 1 and the mean of group 2 in the population are equal. Is the null? The alternative is that they're not equal. Well, what it turns out is you actually, because these are matched from 1 to 2, we actually can just say, what's the difference between them? So what we actually can start working with is the difference score for each subject. So you can take time 2 minus time 1, and that's just going to be your difference score. So if I scored a 10 at time 1 and a 12 at time 2, my difference score would be 2. What that means is now our hypotheses are just based on the difference score. So we're just saying the difference from time 1 to time 2 is 0. Or the alternative is the difference between time 1 and time 2 is not 0. And what this does is it makes it equivalent to the one sample t-test that we talked about before. But now we're just working with the difference scores. So the mean of the difference scores compared with 0. So we're just going to do a one sample t-test and compare it to the known value of 0. So it just turns into this where you have the difference score mean. So we get a difference score for everybody in the sample, and we take the mean of the difference scores. And then that's divided by the standard deviation of the difference scores divided by the square root of n. So we get the standard error of the mean, which is really just the standard error of the difference score. So the standard deviation of the difference score is no different than what we've worked with before. We're just focused on the difference score instead of a regular variable. So now we're treating that difference score as the core thing that we're actually working with. Our degrees of freedom turns into n minus 1. So the number of difference scores or pairs is minus 1. So the n is the number of people or the number of difference scores. So if we have 12 people, we would have 24 observations. We would have 12 at time 1 and 12 at time 2. But we're talking about difference scores. So in the end, when we're doing the difference scores, we'd only have 12. Assumptions are the independence of pairs of observations. So my difference score should not influence anyone else's difference score. We also have the assumption of normality. And this one is of the difference scores. So the difference scores should be normally distributed. And then we want to have equal n's, which makes sense because if you don't have a time 1 or time 2, we can't get a difference score for you. And so you would be deleted. So the pair, the pre and the post, time 1, time 2, different conditions would be just deleted if you don't have both. One thing to keep in mind is the correlation that we talked about recently. It actually has a little bit to do with the t-test here. So the paired samples t-test almost always is more powerful than an independent samples t-test. In other words, if you can get someone to do a pre-post, you're going to get more power than having 2 individuals in independent samples. Which means you're more likely to reject the null when it's actually false, and it requires fewer subjects. So there's a trade-off here where you have to get people to take more tests, so they need a time 1 or time 2, or they need a measure in this condition and then another condition. But you're going to have more power with fewer subjects. So one thing that's interesting is the degree of correlation between the scores for the 2 groups is related to the size of the difference between the paired and independent samples t-tests. What this means is, let's say I bring in a group and I test them from pre-test to post-test. I have 2 options. I could use an independent samples t-test to test for differences, or I could do a paired samples t-test. And the difference between those 2 tests, their t statistics that actually come out, is going to depend on the correlation. So if the time 1 and time 2 are really closely correlated, there's going to be a bigger difference. In other words, the stronger the correlation, the better it is to use a paired sample t-test. If the correlation is really, really small or 0, so if we wait like years between pre-test and post-test, then using an independent samples t-test might be just about the same as using a paired samples t-test, because we gave it so much time that the correlation between time 1 and time 2 isn't going to be very strong. But in most cases, you're not going to be doing that. You're going to be testing them, doing something, and then testing them pretty soon after, maybe within a couple weeks at the longest. So you're going to have more than likely some sort of correlation between them, and that means the paired samples t-test is going to be more powerful. So in other words, when R is 0, in other words, there's no correlation, they become the same thing. The paired samples and the independent samples t-test is identical. When the correlation is positive, which is going to be very common, the denominator reduces, leading to a larger t statistic. In other words, the paired samples becomes more powerful. When the correlation is negative, then you would actually be better off using the independent samples t-test. But note, it's going to be really rare to have a negative correlation with paired data. It's really unlikely for you to totally switch and not be correlated with your own data, and go even further than that and be so like negatively correlated. It's just really unlikely. So that last case is not very common. So with all that said, the idea is the paired sample t-test is more powerful and better to use when you do have matched pairs and there's some sort of correlation between their pre-test and post-test, or between their scores at any of the conditions. So when it comes to confidence intervals, again, we're working with the different scores. So we have the mean of the different score, and then it's going to be plus or minus the critical t related to the different scores, times the standard deviation of the different scores divided by the square root of n. And then using this for the hypothesis test, it would say our paired sample mean significantly different, and it would be yes when null value not within the CI. In other words, 0 is not within the range that the CI gives us. The answer would be no if it actually is. So if we have 0 within this confidence interval, that means they're not significantly different. If 0 is not in there, then they are significantly different. So let's come back to this example. We used this before in the independent samples t-test, but now let's change up the situation. Instead of independent groups, let's say they were carefully matched into pairs. So we had person in 11 is really carefully matched with person that scored 11 here with placebo. So we matched them based on sex, race, drug history, everything that we can think of that has everything to do with this study, particularly depression prior to the initiation of the study, because that's what we're studying. And then we do the experiment. Now note, carefully matching them can be dangerous in that if they're not actually all that similar, this can really throw off your test. So when possible, you'd want to use the same people from group 1 to group 2. But sometimes an intervention like a drug, it's just not possible. So to do this, we're going to read in the data. We're going to make sure we look at our data to understand what's going on. And then what we're going to need to do is take our data frame. We want to pivot it so it's a long format. We're just going to grab the 2 columns that were in there. So our data looked like this, group 1 and group 2. What this does is stack them on top of each other so that now we have a variable called group, or in this case it actually should be name. So with that fixed, what we have is we're going to take this to longer format, and now we have a name variable, and that's just going to be the name of these variables. It's just going to be group 1 or group 2. And then the value is actually the value that they scored. So what we're doing here is we're just pivoting it to longer format here, and then we're going to do the paired samples t-test with paired equals true. And what that does here is we get a significant p-value, 0.036. The mean of the differences is -5. And the 95% confidence interval is from -9.47 to -0.52. So here, 0 is not contained in our 95% confidence interval. It goes from -9 to -0.52, so it doesn't have 0 in it. So that also tells us that's significant, in addition to the p-value itself. Another way that we can do this is we actually can just calculate the difference score on our own. So again, we read in the same data, and instead of reshaping it, we can just say group diff. We're just creating a new variable called group diff, and it's just group 2 minus group 1. And then we just pull that one out. And then the t-test is just a single samples t-test comparing to the value of 0. And if we do that, we get the exact same results. This time it's a +5 than a negative, and this is going in the positive direction. But it's still going to be the exact same numbers. what that basically tells you is that when we did group 2 minus group 1, that meant when the difference is 5, that means group 2 was higher. Back here, it must have done group 1 minus group 2. Naturally, in the paired t-test, that's what it does. A few other things to think about are the effect size. So we use Cohen's d. It's the same as a one sample t-test, just with the different scores. We also have eta squared, which is going to be using the different scores, or the t statistic. We also have power analyses that we can do with this. Very, very similar to what we've done before, with the same ideas of calculating post hoc power or a priori power to tell us the sample size we need, or the observed power that we saw. As a reminder, this goes along with all the other discussion we had with power analyses. It's just specific to different scores in this case. Now note some weaknesses when it comes to the paired samples designs. Now, what we have, because we're using the different scores instead of two independent groups, our degrees of freedom is actually going to be smaller, which generally means, especially with smaller sample sizes, our critical value is going to be bigger. So our reduction in degrees of freedom for the critical value means that our t-statistic needs to be bigger in order for it to be significant. Another thing that can be hard is sometimes we have a lack of a control group. We're going to talk about mixed designs with ANOVA later on. But with this specific design, it can be hard to incorporate a true control. And that can make it really hard to know if changes from pre to post, or time 1 to time 2, or from one condition to another has to do with something other than the intervention itself. If samples are not truly matched, the results will be spurious. So if you really actually have independent groups, but you're treating it as a match group, the different scores are just random, and your results are just going to be crazy. So if you don't have match groups, do not use this design. Do not use this test. So some alternatives: when you don't have normality, you can use what's called the matched pairs Wilcoxon test. You can also use what's called the binomial sign test for two dependent samples. I haven't used that one in the wild personally, but it is a great alternative. And you also can use sample reuse methods. You can use exact tests. They're a very specific type of statistical analysis. Or you can use randomization and permutation tests. These are all really useful, particularly when you have a violation of normality in your data. So that's it for this lecture. If you have questions, please post them to the discussion board. We can talk about any of this. The thing that I'm really hoping you walk away with is that the paired designs is a really powerful way to use data. If you can get people to have a pre-post or measure them in two different circumstances, it can be a powerful way where you don't have to get as big of a sample, and it can provide really important information to help you understand what is actually going on in your data.